Greetings, everybody. Let's kind of come back again and continue our discussion of normal vectors, binormal vectors, and tangent vectors. And so, kind of reviewing where we left off in the last video, we had our unit normal vector, which was going to be parallel to our derivative of the unit tangent vector with respect to arc length. Now, parallel, remember how they were related. It was just the unit normal times the curvature. And so, again, kind of applying this property that we've talked about several times before, that we take the dot product of the unit tangent with itself, it's always 1. Remember that this is our kind of new notation that we're using just to talk about dot product. And so the dot product of the unit tangent with itself is just 1. It's always going to be of length 1. So we take the derivative of both sides with respect to arc length, and we get the product rule on the left, a 0 on the right since it's a constant. And kind of putting these things together, because our dot product is symmetric, we get a factor of 2 divided by 2, and so our dot product of the unit tangent with its derivative is going to be 0. And so that t is going to be orthogonal to its derivative with respect to arc length. And so we have that the normal vector, the unit normal vector, is also going to be orthogonal to t. That we've got the angle between those two vectors as being 90 degrees. All right, so now let's bump things up into three-dimensional space. So for vectors in 3 space, we can define one more vector to go along with this, and that's our binormal vector. Our binormal vector is going to be the one that's going to be perpendicular to both our unit tangent and our unit normal. So how do we do that? We take the cross product. So our binormal vector is just going to be the cross product of the unit tangent cross the unit normal vector. Now, if we look at the magnitude of our binormal vector, well, that's going to be the magnitude of the cross product. And that one, remember, is just the length of the first vector times the length of the second vector times the sine of the angle in between them. Well, we know that angle in between them is going to be pi over 2. T is a unit vector, n is a unit vector, so this whole thing just becomes 1. So what do we get? We get a third unit vector. So our binormal vector is going to be our unit vector that's going to be orthogonal to both t and n. Okay. So what this gives us now, we've kind of got this triple of vectors in three-dimensional space. We've got the vector t that's going along the direction of the curve as the unit tangent. We've got n that's kind of being perpendicular, that's giving information on kind of how this thing is curving if it were in the plane. And then finally we get this vector b. So let's talk a little bit about what this binormal vector does. Okay. Well, since our tangent and normal vector are orthogonal, if we take the dot product of those things, we get 0. And so, again, taking the derivative of those, we're going to get something that looks like the product rule on the left and 0 on the right. So here what we have was the dot product of the unit tangent, derivative of the unit tangent with the unit normal. Well, our unit tangent, a derivative of the unit tangent, was just our curvature times the normal vector. And so what this thing ends up being is just the curvature of the unit vector with itself. We can pull that curvature to the outside. This is a unit vector, so this is the square of the length, but that length is 1. And so all of this thing just reduces to our curvature kappa. So kind of what we've got now is the inner product of the unit tangent with the derivative of the unit normal plus the curvature is going to be 0. Okay, so now kind of coming back, let's review a little bit about projection of vectors. And so remember that we had this vector projection formula, that if we had one vector v and we had another vector u, and we wanted to get the magnitude or how much of the vector u is going to be in the direction of v, that was what we meant by our projection. So the projection onto v of the vector u was just going to be the dot product of u and v divided by the dot product of v with itself. this was our scale factor that scaled our original vector v, because remember what this thing was. It was supposed to be a vector in the direction of v. And so if we're kind of in this special case when v is already a unit vector so that its dot product with itself is 1, then this formula just reduces to the projection being the dot product of the vector u with the vector v times the vector v itself. Now what that means in this case is that the derivative of the normal vector with respect to arc length, what we have is kind of the magnitude of the projection of that thing, because t is a unit vector. The magnitude of that projection is just the negative of the curvature. And so what we have is the projection onto the unit tangent of the derivative of the unit normal is just going to be negative of the curvature times the unit tangent vector. And so what this gives us now is if we take this vector, so this vector dn ds, we don't know really what that thing is, but we can talk about the orthogonal complement of that is really nothing more than the vector minus its projection. So if we take our normal vector, so the vector we're interested in, this dn ds, we take out this projection that we have, and what we're left with is this vector that's going to be perpendicular to our unit tangent vector. And so what this thing is just kind of this remainder vector that's left over, our dn ds minus our projection. So our projection was the negative kt, so when we move it over it becomes positive. So this is actually our orthogonal complement of dn ds when we take out our projection that's in the direction of t. Now, where we're going with this one, we'll kind of save that one for the next video, and I will see you guys then.